Okay, so we're going to continue now looking at energy. Specifically, this problem, what we're going to take a look at is a problem that deals with work energy theorem. So the one that I've got is listed, Karen has a mass of 55.2 kilograms as she rides up the escalator at Woodley Park Station of the DC Metro, Washington, D.C. Karen rode a distance of 50.2 meters, the longest escalator in the free world. We're also told that the acceleration of gravity is 9.8 meters per second squared. In the online homework system, they use 9.8. In class, we normally use 9.81. Not a big difference. The question is, how much work did the escalator do on Karen if it has an inclination of 28.3 degrees? Now, there are a couple of ways to go about this. We can go through and we can use our work equation where work equals our force times our displacement times cosine of the angle between them. Now, if you want to go through and you want to do this approach, you can. You'll need to draw a free body diagram. She'll be going up an inclined plane, basically, because let me draw a picture on this. Can't believe I'm doing this without that. We're going to assume that there's an escalator, basically an inclined plane going up a hill. It's a motorized staircase, for want of a better term. The number I have, though you may have something a little bit different, is 28.3 degrees. And we have a person who is standing on that and goes up the hill some distance, displacement, I might say, of 50.2 meters. Now, we could go through and we could draw our free body diagram. We could deal with the forces we've got for an inclined plane. As a quick reminder, the thing that I would recommend is we've got gravity down, mg, or I should say f sub g, but it'll be equal to the mass times the acceleration due to gravity. We'll have a normal force that comes up off, like this. And then what you would end up finding, because I believe they say at a constant speed, they may not. In fact, I don't think they do, but we're going to assume a constant speed of this. So they're not speeding up or slowing down. You'll find that there is a force supplied by the escalator up like this. And you could go through and you could find the force of the escalator, F little e, I guess. And it would be equal and opposite to the x component of the force of gravity. And the normal force would be the y component here. You could go through and you could do that. And then you could take that force, you could put it in here, multiply it by the displacement, which is 50.2 meters. And cosine of the angle between them, you could work through the angles. If we have time, I might do a video related to that. But take a step back. There's more than one way to deal with work. When I mentioned work energy theorem, that's the best way to look at this when you've got a problem like this. Work is how we add energy or remove energy to a system or from a system. So, let me ask you this. When Karen is at the base of the escalator, what type of energy does she have? Well, during this problem, she's going to have gravitational potential energy because she's going to go up higher, and she's going to have a little bit of kinetic energy based on her actually moving. However, this is why I said technically it needs to have at a constant speed. We'll see about that in just a moment. We'll ignore any gains she gets in kinetic energy because she's going to have pretty much the same amount as she goes up. But she starts off with zero potential energy due to gravity, and later on she ends up with significantly more. Where does that energy come from? Well, the thing that's actually lifting her up is the escalator. So the escalator is giving her that energy. Again, we can go through and we can find the work by using the definition of work, which deals with forces applied over displacements with some angle between them. Or we could also keep in mind how work fits in with energy. Work is how we change energy. Now, her kinetic energy, for our purposes, won't change. She's going the same speed the entire time, so she has the same kinetic energy. What is going to change is her potential energy due to gravity. So what I'm going to do is I'm going to remind you of something we've talked about before. Delta, what it means. Delta does not simply mean change. You are welcome to say change, but you must remember that it is always final minus initial. So what I'm going to say is this. The work done by the escalator, since it's the thing adding energy to Karen, is going to be her final energy, however much energy she has at the beginning, minus however much energy she had at the beginning of the end minus the beginning, final minus initial. This tells us how much energy she's gained, or technically lost, but in this case gained, and that's the work done, the energy added by the escalator. So this would be my approach, and it's also, when you look at the solutions manual on this, it's actually how they solved it too. You can get this. It turns out that that will be a lot of work, but you will get the exact same thing if you've done it correctly. This one's a little bit easier, so let's look at this. We said at the beginning, she has an energy E naught, and at the end, she has an energy E final. Now, these two are not going to be equal to each other, most likely, because we have a suspicion that the escalator is adding energy into the system. Now, what that means is the energy of our system is not conserved because we don't start with what we end with. So it's not conserved. That does not mean that energy overall is not conserved. Energy in the universe is still conserved. It just means that the escalator is giving up some energy to give it to Karen. It's going from one place to another. Karen's energy is not conserved, but the universe's energy still is, because the energy we give to Karen comes from whatever is powering the escalator, be it electrical energy or chemical energy from some fuel. All right, so we've got some kinetic energy, but we're actually going to ignore that because we know that the kinetic energy at the beginning is also going to be the same thing that we had at the end, because I've mentioned to you that she goes up kind of at a constant speed. The escalator is not speeding up as it goes, and so her kinetic energy is actually going to be the same in both cases. Okay? But we also have plus her gravitational potential energy. So what I'm going to do is this. Since we know that both of these are going to be the same, when I do E1 minus E naught, I'm going to get the following. My kinetic energy final plus my potential energy due to gravity final minus my kinetic energy initial plus, I need parentheses here because we're going to subtract all of this, potential energy due to gravity initial. Be careful with your signs here. We're taking the final minus all of the initial. So even though these are plus, these two would add together, but they're still subtracted off the other. In any case, when I do my kinetic energies, the kinetic energies are going to be the same thing. We don't know what that number is because we don't know how fast she's going, but I will tell you that she's going at a constant speed, which means since her mass doesn't change, both of those values are going to be the same. So her change in energy is just going to be her potential energy due to gravity, which is going to be mg y1 minus mg y0, which is another way of saying mg delta y, but I can do mg y1 minus y0, which is delta y, final minus initial. Here's where we can start plugging in some values. Although there is one other thing that we're going to need to know, because I don't know my y's. Now, you might think that we want to put in 50.2 meters, but remember, since we're looking at this from the potential energy viewpoint, for gravity, I made a big point of saying what gravity cares about is the vertical distance. We've got 28.3 degrees and 50.2 meters as our hypotenuse. If I want to find the opposite side, I'll deal with sine of 28.3 degrees equals my y divided by 50.2 meters. You do a little bit of math with that, make certain your calculator is set to degrees, since we're using 28.3, so I'm going to do sine 28.3. Let me double check that mine is, I left this out. Nope, it's good. Okay, and then I'm going to do times 50.2. I would multiply both sides by 50.2, and I find that my y is equal to 23.8 meters for my problem. This is how high we're going. And while in the work equation here, we would use 50.2 meters if we were doing this approach, where we'd have a cosine of an angle in here, we'd have to solve for all of those. This number is my displacement overall that the force is applied over. What potential energy due to gravity cares about is not the total displacement, it's only the vertical displacement. So, if I plug this in, Karen had a mass of 55.2 kilograms times, they told us 9.8 meters per second squared Normally we use 9.81, but that's okay. And I know that my final height is 23.8 meters above my initial height, which I'm just going to call 0. That'll be my reference point. Okay, so I multiply these out times 9.81 times 55.2. When I do all of this together, I find that my E final minus E initial, which is what we found here, is equal to 12,890 joules to 4 significant figures. And since this is my delta E, final minus initial, it is also equal to my work. That's how much energy was added in. I had some energy at the beginning, and at the end, I have nearly 13,000 joules more. That has to be transferred in. That's what work is, the transfer of energy. Let's double check our answers. Survey says 12,874 is what they have listed as the value answer. That's a rounding error thing, but it turns out that this will also be accepted. Again, you can go through and solve this with the work energy approach. If I have time, I have couple other videos that I want to do, so I don't want to lose time on that. This is the better way of going about it, but both of them will work just fine.